At this point, we are ready to talk about the idea of negative exponents. So notice so far in these lessons, we've discussed only positive integer exponents and 0 as an exponent. So really, we've kind of stuck with this idea that an exponent means the number of factors multiplied together. And so we think of the exponent as something we can count. Now we're moving a little bit outside of that. We're expanding the definition where the exponent can be a negative integer as well. And we have to ask ourselves exactly what would this mean? What would it mean to have a negative integer as an exponent? We had b to the negative 3. What on earth would that mean? Well, as mathematicians often do, we will take a pattern that we already know and understand and extend it to cover something not yet covered by the rules. This is something that happens in mathematics over and over again. In this particular case, we know the division rule for powers. That's something we've talked about in the previous video. We know that if we made the denominator exponent smaller and then the denominator exponent bigger and the numerator exponent smaller, then we would get a negative result for the subtraction, and that would give us a negative exponent. Let's look at a numerical example with a higher power in the denominator. So, for example, suppose we had 13 to the 4 divided by 13 to the 7. Well, the power in the denominator is clearly a larger power. Well, if we just follow the division of the power pattern for exponents, of course that tells us to subtract the exponents, we'd get 13 to the 4 minus 7, or 13 to the negative 3. All right, that's one way to approach this. Now let's go back and think of this in terms of the fundamental definition of an exponent. The fundamental definition of an exponent is that 13 to the 4 means that we're multiplying 4 factors of 13 together. And similarly in the denominator, we'd have 7 factors of 13 multiplied together. And so what we have here, of course, we're going to get some cancellation. We're going to cancel 4 of those factors of 13 in the numerator and the denominator. They're going to cancel. When we cancel, we're going to be left with 1 in the numerator, and we're going to have 3 factors of 13 in the denominator, and of course this would be 1 over 13 cubed. Now compare those two results. One way of thinking about it, we got 13 to the negative 3. Another way of thinking about it, we got 1 over 13 cubed. If these two equal the same thing, they must equal each other. And this suggests that b to the negative n equals 1 over b to the n. So that is the exponent rule. That is the rule for negative exponents. And this is one way to think about it. Here's another way to think about it. Any negative number can be written as 0 minus the absolute value of that number. For example, we could write negative 3 as 0 minus positive 3. In general, negative n, we could write that as 0 minus n. So this means that b to the negative n, we can think of that as b to the 0 minus n. Well, if we have subtraction in the exponents, that means divide the powers. That must mean b to the 0 divided by b to the n, and of course b to the 0 is 1. And so this would be 1 over b to the n. So this is another way to think about why b to the negative n equals 1 over b to the n. Here's another way to think about it. It's good to have as many ways to think about this as possible because it's a somewhat anti-intuitive idea, thinking about negative exponents. It's really good to have a variety of ways to make sense of it. Imagine a sidewalk of exponents. So notice that every number on the top equals, the power on the top equals the output on the bottom. So that's true for every box here. And as we move to the right, what's happening is we add 1 to the exponent. So the exponent is increasing in the green row at the top, and we multiply by a factor of 2 in the bottom row. So to go from 1 to 2 to 4 to 8 to 16, each step we're multiplying by 2. That's what happens when we move to the right. Each step to the left, we subtract 1 from the exponent, and we divide by 2 in the bottom row. So if we start at 2 to the 5th and 32, as we start taking steps to the left, we're subtracting 1 from the exponent, and we're dividing the purple number in the bottom by 2. What would happen if we walk to the left of 0? So here's our sidewalk again, but we just extended it to the left past 2 to the 0. Well, again, going to the left, the exponents go down by 1 each step in the top row, and the numbers get divided by 2 each step in the bottom row. So in the top row, that exponent would go down from 0 to -1, and we would divide 1 by 2, so we'd get 1/2. 2 to the -1 equals 1/2. Now take another step. That would be 2 to the -2 equals 1/2 divided by 2, which would be 1/4. Take another step. 2 to the -3 and 1/8. Then 2 to the -4 and 1/16. And you see this same pattern continues perfectly for both the positive and negative numbers. In many ways, the exponent rule fits with the other exponent patterns very, very well. And the more you appreciate how they all fit together as a seamless whole, the more you will really understand this rule. So the rule, of course, is b to the -n equals 1 over b to the n. So another way to say this is a base to a negative power is the reciprocal of that same base to the positive power. This means that a negative exponent on a fraction will be the reciprocal to the positive power. So I have the fraction p over q to the -n, that will equal q over p to the positive n. That's a really handy shortcut to know on the test. A negative power in the numerator of a fraction can be moved to the denominator as a positive power, or likewise from the denominator to the numerator. So for example, if I have this fraction and I need to simplify it, well, that d to the -8 in the numerator, if I move that to the denominator, it will be a d to the positive 8. That h to the -4 in the denominator, if I move that to the numerator, it will become h to the positive 4. And so this is the expression now written with all positive powers. So for example, you might be asked to simplify something like this. Pause the video and see if you can simplify this, and then we'll talk about it. Well, of course, the first thing we'll do is we can treat the numbers separately from the exponents. And for the numbers, we'll just factor out the greatest common factor, which is 6. So not changing the exponents at all, just the numbers simplified to a 4 over 3. Now, with that x to the -4 in the denominator, that can move up to the numerator. One way to think about it is it moves up to the numerator, so we get an x to the 12th times an x to the 4th in the numerator. Another way is just to think about the law of division, and we get an x to the 12 minus -4. And of course, 12 minus -4 is the same as 12 plus 4. Of course, with the y's, we just have ordinary division of powers. So the y's, that's the easiest to handle. That is 9 minus 3 y to the 6. Then we treat those x's. We move it up to the numerator. This is one way to handle it. We move it up to the numerator. Of course, then we add the powers, and we get 4/3 x to the 16th y to the 6. And that is the most simplified we can make this. Here's a practice problem. Pause the video, and then we'll talk about this. Okay, so we have to rank things from smallest to biggest. The test loves these ranking questions. So first of all, 1/3 to the -8. Well, what does that mean? That's the same as 3 to the positive 8. Now remember that 3 to the 4th is 81. So let's approximate that as 80. 3 to the 4th is approximately 80. Well, 3 to the 8th is going to be 3 to the 4th squared. So that's going to be approximately 80 squared. And 80 squared, that's up above 6,000. So that's a relatively large number. That's what 1 equals. 3 to the -3rd. Well, this is 1/3 to the third, and so this is 1/27. Okay, so that's clearly much smaller than 1. And then if we look at the last one, 1/3 to the fifth, well, we don't even have to calculate the value. 1/3 to the fifth we know is going to be smaller than 1/3 to the third. And so that means that 3 is the smallest, 2 is the middle, and 1 is the biggest. So in order, it's 3, 2, 1, and this is answer choice E. In summary, b to the negative n equals 1 over b to the n. A base to a negative exponent is 1 over the base to the positive of that exponent. A fraction to the negative n equals the reciprocal to the positive n, so we can flip over a fraction and get rid of the negative in the exponent. And exponents switch from negative to positive when we move them in a fraction from numerator to denominator, or vice versa.